in earlier. So like at the beginning, if you can, so that way I know. Okay. All right, ladies and gentlemen. So I am going to backtrack a little bit to yesterday because I feel like we went a little too fast, and you do not need to see the under part of my stairs. Okay. I'm gonna work on specific heat more. Okay, and we're gonna watch a couple of videos and stop the video and come back. Okay. The first thing with specific heat that we were working on was that Q equation, that Q equals MC delta T. Yes? You guys remember that from yesterday?
Yeah.
Okay.
Yeah.
So that Q equation, all right, there's going to actually be 3 different Q equations. It depends on if you're going through a phase change or not. All right. But if we're talking about specific heat, the only one that you can use is the MCAT one, the MC delta T. It kind of spells out MCAT. Okay. So I want to prove to you guys a couple of things. First of all, you guys all have your reference tables out, yes?
Yeah.
Take out your reference tables, and I want you to have it handy. So if you have the hard copy, it would be better. So you can leave it, or if you have the review book, for those of you who actually went and bought the review book, in the back, right before the vocab, I mark it off with a little paper clip here. But there's an entire section that's just the reference table. So if you want to buy the review book, like I said, it's not mandatory, but I highly suggest that you have a hard copy for home, because then you don't have to worry about printing out a hard copy of your reference table and the regencies that we're going to be doing for practice, so on and so forth. So we're on page 1. In the top right-hand corner, you see where it says specific heat of common materials, right? Okay. So that's this one. Okay. This is in the top right-hand corner of your reference table. Okay.
Sorry, I'm not sure what you want me to.
Yeah, you're annoying. Okay, so Jared, you're in charge of telling me what time it is. Cool.
What time do you want to know?
12:25.
Okay.
Timer for 12:25. See if it'll work. Okay, so all right, just in case you're my backup. Okay, so basically with specific heat, right? We can see that all of these different materials have a specific heat value. Right? We can see it. No big deal. Now, the higher the specific heat, the more energy needs to be absorbed to heat up that material by 1 degree. Okay? So water needs 4.18 joules of heat in order to increase its temperature by 1 degree. Whereas lead only needs 0.13 joules of heat to increase by 1 degree. So you guys are not really responsible for this class to know how to do the math. So I'm going to show you it. All right. Here I have 10 grams of water and 10 grams of lead. With me so far? Right? Just 10 grams of water and 10 grams of lead. So I have the same amount of lead as I do water. I want to change both of them by 50 degrees. Good so far? Yes? You can follow along with this guy so far?
Wait.
Yes.
The delta T temperature change in temperature?
Yep.
Okay.
Yep. And C is the specific heat capacity. Okay. So right now, right, I wrote out the formulas. All I want you to do is just pay attention to the stuff above the line. Okay. That's what's given to you. All right. You're given that you have 10 grams of both substances. You're given that you want to change the temperature by 50 degrees. And you're given, according to page 1 of the reference table, their specific heat values. Okay. What I did was I used the formula to determine how much heat would be necessary to increase both of them by 50 degrees. Okay? To increase water by 50 degrees, you need 2,090 joules of heat energy. Unlike lead, where you only need 65 joules of heat energy. So what does that tell me? That tells me that lead is going to reach that 50-degree mark much faster than water will. Okay? It also tells me that, okay, so what do we conclude? You guys know this means therefore, yes? 3 dots? Right? You guys all did proofs, right? At some point in your life?
Yeah.
Right?
No.
And the 3 dots in a triangle means therefore?
No.
No.
You'll learn something new every day.
Yes.
3 dots in a triangle means therefore. So it's like in conclusion, therefore. Okay? Water heats up and cools down much slower than lead. Okay? That's what that means. So the water needs so much more heat energy than lead does in order to heat up or to cool down. Because all of this has to do with both the heating and the cooling of a substance. Okay? What my plan is that we were supposed to do a lab on this, but we're home. So I'm going to school today to grab all of the materials I need to be able to do this with you tomorrow in class, I believe. We're going to see. Or I may just demo it.
Do we need anything?
No, you guys don't need anything for this one.
I have a question.
Who is that? Kasmira, I think?
Yeah.
What's up?
So like if water needs like 2,000 joules to like increase heat energy, right? The number is so high. Like, why is that?
It's because its specific heat capacity is also so high. So since its specific heat capacity is 4.18, that means it would be kind of like, you know how some people, this is a really crude, simple way of putting this, but do you know how some people sweat more than others, even though you've been doing the same amount of energy, you've been running the same mile? Like there's some people who come out of gym and they look like they just took a shower.
Yeah.
And then there are some people who look like they've been sipping tea for the last hour.
Yeah.
Okay. So the people who are sweating profusely have a lower specific heat capacity. So it doesn't take them a lot to start, because the whole point of sweating is that you're cooling yourself down, right? So that means their body temperature has increased so much that their body's trying to counteract that, right? So they would be like lead. Whereas somebody who literally gets out of gym and is like, oh, I'm okay, right? Barely breaking a sweat, even though they ran the same freshman mile that you did, right? They would be the ones who have the higher specific heat capacity. Why? Because it takes more energy for them to heat up or cool down. Okay? What I'm going to do is I'm going to show you this little video clip that I found. Okay? It's that Hammocks Middle School guy I was telling you about again. Okay? Can you guys see my screen where it says specific heat and it's a YouTube video?
No, it's still at
No.
it's still at the board where you were drawing.
Okay, hold on. Let's go here. I'm going to override myself here. Good?
Yep.
Okay.
Uh-huh.
So
Yeah.
I'm going to play this with you and I'm going to stop it at certain points and maybe it'll make a little bit more sense.
definition of specific heat. Basically, how much heat energy
Can you hear that?
needs to raise one.
Not really.
Okay, hold on, let me make it louder. It's gonna be super loud for me, but it's okay.
Gram of a substance 1 degree Celsius. Now, an easier way to remember that is basically how quickly or how slowly something's going to heat up or cool off. Now, when dealing with specific heats, every single substance on the planet has its own specific heat. Every substance on the planet heats and cools at its own rate. Something that has a very high specific heat is an example of water. Something that has a very low specific heat, a good example of that is going to be lead.
So this is what I was just telling you, right? Because based on the numbers on the chart, water has a very high specific heat, okay? Where according to the chart, now remember, this is all about the chart. This isn't in real life necessarily. There's other stuff that might be lower than lead or might be higher than water, okay?
Now, the reason why we gave you those two substances because they're going to be the two extremes on your reference table, page 1, specific heat of primary materials. So make sure you check out my podcast on that page as well. So let's see what high specific heat means. It's all about how quickly or how slowly something's going to heat up. Something with a high specific heat heats and cools extremely slowly. It needs a tremendous amount of heat energy to heat and cool off.
So this is what I was just saying. So water, you need an extreme amount of heat to heat up, and you need to release that heat to cool down. So it's going to take water a long time to heat up and to cool down.
Well, we gave you the example of water, and the reason why water has the highest specific heat of any substance on the planet is first off, it's highly reflective. So it takes a long time for that energy to be absorbed, especially when water is going to be reflecting sun's energy off its shiny surface. And B, it's transparent. Not only does the surface of the water get heated, the middle of the water gets heated, and even the bottom of the water column might get heated as well. So there's a tremendous amount of volume that needs to get heated up. That's why water has such a high specific heat. Heats and cools very slowly. And you can see here that 4.18 joules per gram is going to be the unit here. So when you're dealing with specific heat, basically how that's going to be interpreted is water needs 4.18 units of heat energy, or joules, to raise 1 gram of water 1 degree Celsius. Now we compare that with a substance with a very low specific heat, means it's going to heat and cool extremely quickly. The example we gave there was going to be lead. We know lead is a metal. Metals tend to be extremely good conductors of energy. So lead and really a lot of your metals are going to heat and cool extremely quickly. That's why your frying pans, for instance, are going to have plastic handles or rubber handles. You don't want a metal handle, very simply because the pan is going to heat up very, very quickly. So when we talk about low specific heat, take a look at the heat energy here, 0.13 joules of heat energy to raise 1 gram of lead 1 degree Celsius. So significantly lower than water. So keep going with the water aspect here in terms of its high specific heat. The thing is with water is that your oceans, which are a major, major volume of water, take all summer long to heat up, and they take all winter long to cool off.
Do you guys know what this weekend a lot of people did?
No.
Does anybody know this thing that happens usually on the first Sunday of February, right before the Super Bowl? There's a bunch of people that go to the beach. You know what that's called?
Sweet spot?
No, it's called the polar bear plunge. All right. And so basically, usually it's for a good cause. People will raise money for a different charity every year. And they basically, it's a giant bet. So it would be like, Jared, if I said to you, I bet you $25 you won't run into that ocean on February 4th. Okay. And then Kazmira jumps in and says, you know what? I'll take that bet. Here's another $25. You won't do it. Okay. And people, that's how people raise money. So basically, on that day, you'll go and run into the ocean. Well, a lot of the people who go into the ocean, give me a sec, Jazzy. Okay, go put it in the sink, please. Thank you, baby girl. Who run into the ocean say that the water is warm, but it's the middle of February. So we know the air temperature is cold, right? That's why it's a bet, but you're really raising money for a charity. The reason why that the water is warmer than the air is because of this specific heat. It's because of the fact that water has such a high specific heat. It's going to take them the entire winter for the water that absorbed all that sunlight all summer long to now cool down. Okay? That's also why if you go to the beach in May or June, right? You're like, yeah, it's a really nice sunny day out. It's like 80 degrees outside. I'm going to the beach. Awesome. And then you go to the water and you go, nope, not going in. Why? Because it may be really warm outside, but that water has not had enough time to absorb that heat. So it takes almost the entire summer. And sometimes the warmest temperatures in the oceans are September, which is also why we have hurricane season in August, September, October, November, because you have these warm oceans, which we'll get to later on in the year. Well, not next unit, I should say. Okay. But it's because of that the oceans are going to be warmer. It took all summer long. It was just taking in the heat, taking in the heat, taking in the heat, taking in the heat over and over and over and over again. Right? All it did was take in heat for all of the summer months. But now, as the temperature is cooling down around it, it needs to release that heat. So if it took 2,090 joules of heat to increase the temperature of the water by 50 degrees for like a small amount, 10 grams of it, okay, it's also going to have to release 2,090 joules of heat to reduce it 50 degrees. And that's only a small amount.
Because water has such a high specific heat, the oceans really tend to heat up from February all the way to about August. It really takes a significant amount of time for our oceans to heat up. So your summertime temperatures tend to be a little bit cooler in the water, which means that the air above it tends to be a little bit cooler. Well, it takes all winter long to cool off, basically from August to about February. So when you're dealing with a significant amount of heat energy that's being retained throughout the winter, those oceans tend to be a little bit warmer, meaning that the air tends to be a little bit warmer. What's important about that, that's going to have some major climatic issues regarding our coastal regions. We compare that with land. Land, which is extremely dark in color, is going to heat very quickly in the summer and get very hot. It's going to cool off very quickly in the winter. It is going to be quite cold. So very simply because dark colors tend to not only be good absorbers, but they're also good radiators of energy as well. So very, very different specific heats between ocean and land. And the big thing here is that the specific heat of oceans and the specific heat of land are going to have major climatic issues regarding cities that are located in those regions. So what will happen here is that you can compare coastal temperatures versus inland or continental temperatures, and you'll see a stark difference between them.
Okay, so what I would do, guys, is I would write this down. Okay, because I know you're already taking notes on this video because it's a video that I'm showing you in class. Okay, but I would, do I want to get into this? Coastal versus continental? Yeah, we can. Okay.
This is very simply because water is going to moderate the temperature. Because water takes all summer to heat up and all winter to cool off, the water tends to moderate coastal region temperatures. So these cities along the coastal regions tend to have quite different temperatures than areas that are much more inland, far away from large bodies of water. So let's take a look.
I know some of you guys need me to go back. So guys, this is why even, was it yesterday or the day before, right? They were talking about this storm that was coming through. And in the upper parts of New York, they always say north and west of the city, right? Because they're more inland. They'll have colder temperatures. They'll have more extremes where it's super hot and super cold because they don't have water to help with that temperature. Here, because even though you live in Queens, you're on Long Island, you're surrounded by water, okay, it will actually end up being more of a rain than it is a snowstorm. That's why north and west of the city always gets slammed with snow, whereas we're like, it's raining. Why do they have a snow day? I don't understand. Okay, it's because we're surrounded by that water.
From large bodies of water. So let's take a look. Your coastal regions tend to have very cool summers. very simply because the oceans are quite cool. The air above the oceans tend to be quite cool, which are going to cool off the cities that are somewhat coastal. If you've ever been to the beach during the daytime, you'll get a nice breeze off the ocean. That's very simply because the ocean water tends to be able to be cool. Well, coastal regions tend to have a little bit warmer winters because the high specific heat of water retains the heat energy from the summertime, doesn't want to give it up. So if the oceans are a little bit warmer, the air's a little bit warmer. So what'll happen here is you do not get a huge difference in temperature between winter and summer. They tend to be a little bit more moderated because the water moderates the coastal regions. You compare that with your continental or more inland regions, because land heats up so quickly, you're going to have really hot summers. Because land cools off very quickly, you're going to have very cold winters. So you will have a very big difference between your summertime temperatures and your wintertime temperatures. So when you look at a graph like this, you're comparing two cities. City A is going to be the solid line, and city B is going to be the dotted line. You notice that city A has a huge difference between your average temperature from winter to summer compared to your city B's temperatures from winter to summer. City B is much more moderated. That must be closer to the water.
So we would be like city B. Okay. We have our temperatures don't change extremely from month to month. Okay. Inland ones, the ones that are further away from the water, are going to be on the extremes. They're going to have extremely hot summers and extremely cold winters. Think of places like Arizona in the middle of the summer. You can fry an egg on a sidewalk. That's no joke, because the temperature is super hot, but it's called a dry heat because they're not near any water. And then it also gets super cold, believe it or not.
City A has a huge difference in winter to summertime temperature, means it must be a little bit more inland. And again, you just take a look at some current values here. We're going to kind of focus on some wintertime temperatures. If you notice in the northeast part
That's where we
of
are.
the country here that I've just circled, you notice that some of your temperatures, notice that you have a 56 compared to a 48, so your 56 is a little bit warmer.
Notice where that 48 is, though. Notice it's not near the water, right? The extreme temperatures are going to be inland more.
The 48 is a little bit cooler, a little bit more inland, tends to be a little bit cooler. Well, you compare that with some summertime temperatures in that same region. Notice now along the coastline is about 62, a little bit more inland is about 73. They're exactly flip-flopped in terms of your temperatures. Coastal regions tend to have cooler summers. Coastal regions tend to have a little bit warmer winters. Your inland regions tend to have a little bit of a warmer summer, and your inland regions tend to have a little bit colder winters. So your coastal versus continental temperatures tend to be a little bit opposite. So that's about it for now. Hopefully we cleared up some.
Okay, so who's got a question for me right now?
So continental regions are like the opposite of coastal regions.
Yes. So continental means they're away from the water, right? You know, when you say continental United States, it means you can drive from New York to California, right? Coastal, I mean, even though they have coast on them, but continental United States means it's on the continent inside. So when we're talking about continental, you should be thinking of, going back to his picture here, right? You should be thinking of the more inland. The further away you get from the water, the more extreme your temperatures are going to be. So the reason he was circling this part was just to show you the difference between where we are on Long Island and, you know, north and west of the city. Okay. It also, something that also comes into play is your latitude. Okay. So if you're going to compare it, you have to compare it to something that's near you, pretty much on the same latitude line. Because if I compared us to California down here, it's not always going to be the same because they're also closer to the equator, which means that their temperatures are going to be higher. It doesn't matter what time of year it is because of the sun, right? Right. If we go back to the winter temperatures, there's our winter temperatures, right? So looking here even, right, more into the continental United States, more inland, away from the water, we have 42, like we have lower temperatures. And then if you compare it to their summer, they're much higher, right? They're even higher than us at 79. So the spread between the two, if you look at the summer temperature and the winter temperature for the inland states, it's going to be a big difference, or a bigger difference than if you look at the ones that are on the coast itself, right? Because the summer temperature that he's pointing out right now is 62 degrees for us, but the winter temperature is only 56. So that's only a difference of 6 degrees. Just happens to be he's taking it from March of 2010. Okay. Whereas over here, it's 49 degrees in the winter, but it's 79 degrees in the summer. So that's 39 or 30 degrees difference. So that's a big difference. That's what that means, is that like their summer temperatures are going to be much higher and their winter temperatures are going to be much lower. Okay. Before I move on to the rest of, we're going to do the land versus water experiment tomorrow. Okay. But I want you to predict. Okay. I want you to predict what is going to heat up faster, land or water. I want you to think about these things, okay? And I want you to be able to explain why. And then also what is going to cool down faster, land or water. And I have one more video to show you, which I just showed my daughter and she loved it because it's for kids, but I feel like this is such an extreme topic that I feel like it will help you guys to watch this. So just keep in mind those two things, land versus water. Where did you go? Where did my thing go? No, here we are.
Hey guys, what's up? So I
Holy
am super
commercial.
into this website right now. It's Generation Genius. And they cover all of the science.
24. My bad.
It's okay. So in conclusion, guys, right? Things that have a higher specific heat are going to need more energy to heat up or cool down. Okay. Things that have a lower specific heat are not going to need as much, which is why if you've ever been to the beach at night, she was just talking about the beach during the day, right? If you go to the beach at night, right, the sand is nice and cool, even if it's the same day, but the sand is nice and cool. And when you put your feet in the water, because you shouldn't go swimming at night because you can get lost very quickly, you put your feet in, the water feels nice and warm. So this is all about specific heat. If you guys have any other questions, you know you can shoot me an email. Does anybody have a question right now?
No.
All right, guys. So that's perfect timing because that is the end of our show for today. I will see you guys tomorrow.
Bye.
Bye, Miss Gonzalez.
Bye.
Bye.